Right, I'll make a start, it's getting quite late. So this is some work that we've been doing over the last couple of years. There's Ambar and Kandu, whom everyone's familiar with, and Carlo Berenghi's also been involved as at Newcastle. He's probably more well known for his work on quantized vortices, but he's got varied interests, so he's been very useful in this project. So in a lot of the stuff that we've seen over the last week and a half, people have been using flux ropes to help conceptualise ideas, this Zordovic stretch twist fold. So what we've got is a dynamo where the only diffusion that's acting is reconnections, and our magnetic field is confined to thin flux tubes or flux ropes. Let's see if this works. I'll skip through this because we're quite late and you'll see what's coming up anyway. So very quickly, we've got this dynamo effect that's been introduced, and the main point from this slide is just that we're concentrating on the fluctuation dynamo, the small-scale dynamo, for very good reasons, really, that we'll come on to later with magnetic helicity in our model. So we're considering the evolution of a weak seed field in a random, we're going to be using a turbulent light flow. So what you could do, what people do in the literature, is to solve both these equations either by making approximations analytically or by, on a computer. Axel's obviously done some simulations of the pencil code. Alex Shekachikin has finite difference or spectral codes solving these guys here. But we're not going to do that. We're going to consider rarefied plasma, where the MHD equations that have been covered in this last week and a half may not be valid and plasma effects start to become important. There's one paper here I make a reference to where Axel and Graham, who's at Newcastle, just changed the diffusion operator and considered hyperdiffusion. It was with a helical flow, but showed that the dynamo saturated at a higher energy. That's correct, Axel, yeah. We kind of go to the limit of, well, Rm tending to infinity, I guess, and just look at diffusion only acting in reconnection events. And as I've said, our magnetic field is confined to thin flux tubes which are frozen into the flow. So the next couple of slides, I'll cover the flow, but I'll go through it quite quickly. If anyone's interested in this, they can always come and find me. We don't solve Navier-Stokes on a mesh for a couple of reasons. Laziness, and this is very easy to implement numerically, and our code is Lagrangian, and so it's quite nice having this analytic formula for the velocity field because we don't have to interpolate from a mesh or anything like that. So it's just a random summation of Fourier modes, and you are free to impose any slope on the spectrum that you want. And so in all the simulations that I cover here, we just go for a Kolmogorov -5/3 spectrum. Like I say, if you want any details, there's either a paper there or come and find me. It was used by Louise Wilkin, who was at Newcastle, to drive the dynamo, and was used to study the morphology of the fluctuation dynamo. The flow can be this flow can be easily modified to be periodic, which is useful for when we're solving the induction equation, which we do later. Just for periodic boundary conditions. Okay, so that's enough about the flow. Oh no, it's not. I've got a little bit more. Here I've got some snapshots. They weren't produced by me, so I don't really know much about the DNS, the parameters and things. All I know is that it's a similar Reynolds number, and the key point is just that there's an absence of structure in the KS flow compared with what you get at DNS. But these are courtesy of Benjamin Favier, who's Claude Campbell's student at Lyon. Also with the KS flow, I've got these you can modify the wave numbers, and you can actually simulate the effects of rotation here. So we've got these columnar-like structures, or stable stratification, where you've got these sort of pancake-like structures. So it's quite a versatile flow, and it's very quick to compute, and so it's very good for our simulations. We also have used, just because people have not often seen this flow before, we've used the ABC flow as well, which people in the dynamo community are more familiar with. So any results that we present are not because we use this weird flow that no one's seen before, but a result of the dynamo and not the velocity field. Okay. So what we've got is just a numerical model for flux tubes. So we discretise these into fluid particles, which move with the flow. We keep the separation of our particles smaller than the inner length scale, which you can easily get from this KS model. The flow exhibits Lagrangian chaos, and so these particles tend to move apart, stretching the flux tubes. And so just to maintain resolution, if two particles on this flux tube become further than a certain distance, we pop a new particle in. Now to take these really from discrete lines to magnetic flux tubes, we've just got to account for local stretching. And I think Kandu in his first lecture put these arguments on the board, that really it's just a case of having the rate of change of magnetic flux is 0, and so you can make these arguments that just gets you down to the fact that the magnetic field times the length of the flux tube has to be constant. So if you introduce new particles, the field line's been, or the flux tube's been stretched, and so the magnetic field has to increase.
Sorry, Andrew. A is area, right?
Yes, sorry. A is the cross-sectional area of the flux tube, but it just pops out and gets you down to this relationship here. A is the cross-sectional area. So the scheme is something like this, nice and simple. These numbers here are just the field strength. It's just a numerical flag that we have attached to each particle. We also know the particle in front and the particle behind, so we can draw a line that represents our magnetic flux tube. And if there's localized stretching, its length is doubled, and so we increase the field strength flags on these two particles here. And we can also show that this is fully reversible as well. So what we did was just a nice little test of this. A Gaussian shear flow, very simple velocity profile. We put magnetic diffusivity to 0 in the induction equation, and it can be solved analytically. In fact, it's that straightforward that Anvar sets it to his fourth-year students to solve, I believe, as a homework. So you get this solution that pops out, and you can just see that B increases linearly with time for given positions of Y along the profile here. So what we do is pick a value of Y nearest to maximum strain, maximum shear, although you can do it all the way along, and we just test that we get a decent agreement between our code and what you'd expect from this relationship here. This is a snapshot of the run. I don't know what happened to the numbers that were down the side of this colour bar, they've vanished, but they're not important. Basically, where it's blue, the field strength is quite weak. Where it's red, the field strength is quite strong. So as you'd expect, in the areas of highest shear, the magnetic field strength is strongest. And what we do is we pick, I can't quite remember what the value is, but we pick a value just from around here, and we plot its value of field strength against T. Once we get to a certain time, we reverse the flow just to check our algorithm is fully reversible, and we compare it to the expected field strength from our students' relationship. And what we get is this here. So you can see it's not a spectacular agreement. We have these jumps just because the field strength is doubled. And so the field strength is always a power of 2. In fact, what I've been doing recently, just playing around with, is just smoothing this, the little Gaussian smoothing at each point, and it actually converges very quickly onto this line if you do that. But the main point is that you match the field strength, and then when the flow is reversed, our little algorithm is fully reversible. With this flow here, it's kind of exposing the biggest flaws in the model, because you're just stretching in a continuous in the same direction, and new particles are inserted all at once. So in the random flow that we consider, it may not be quite so bad.
Does the code lose particles?
Yeah, particles are removed, either by the contraction of the flux tube or by reconnection events, which I'm coming on to now. Yeah, so if there's localized contraction, then this same resolution is maintained, so particles will be lost, so that we're not keeping particles that are not necessary. So in reality, it is not going to be equal to 0, and So resistivity can act at very short length scales, and so we allow our flux tubes to reconnect and release energy in the form of heat into the fluid. So what we do, we've got Carlo on board who's very familiar with these quantized vortices simulations, where the quantized vortices are very, very thin cores, and so they model them as discrete lines, and they also reconnect. And so we borrow a very similar algorithm to what Carlo uses, and we just reconnect on a purely geometrical basis. We then, I'm not going into detail here, but we can reproduce some results from the literature. So flux expulsion, Ambar's already showed you some of the simulations from the code. So you get an initial winding up of the field, and then once the separation of the flux tubes becomes very small, reconnections can kick in, and then the field is expelled from the vortex. We show that no planar flow can maintain the dynamo, so we can put use that into something like the KS flow and show that even though you get an initial growth in the field, in the end it all collapses. And we can also look at growth rates of the dynamo. So if we drive the flux stroke dynamo, which I'll explain a little bit more about the reconnections in a second, but if we drive it with the 111 ABC flow, we get a growth rate of about 0.083. Dork, in a quite a high magnetic Reynolds number simulation, obtained about 0.077, something like that. So we're slightly higher than this value here. Actually plateaus at like Rm greater than 1,000 or something like that. So we're slightly higher than the growth rate in Rm tending to infinity in the induction equation, but it's not too dramatic. So this is the sort of reconnection algorithm that we have. So we've got a resolution along the line, and if two flux tubes become very close, we have a reconnection length scale D0, which we keep of the order of the separation along here, so that we don't have any smaller scales being introduced that we don't resolve. We get a reconnection. The two particles in the middle are removed just so that the length of the flux tubes after the reconnection is less than the length before, and so energy is released. We don't have a boom, unfortunately. And one thing that we do check is just the orientation of the flux tubes. So we just use a simple cross product rule, a dot product rule even, sorry, and just check that two parallel flux tubes aren't allowed to reconnect in the code, and just have some small tolerance on that. So what we do is perform some simulations using the KS flow and also using the ABC flow. So these are just kinematic simulations to begin with. So we set up a random field, just sort of chuck an ensemble of random flux tubes in. We smooth the field, which preserves divergence of BD equal to 0. And we integrate from the same initial conditions, this flux rope dynamo and the induction equation. Oh, my microphone not been working. Sorry.
It is okay.
Is it okay? Sorry. Using a finite distance stream in the induction equation, driven by the same flow, and we're going to consider the energy release rate from the two simulations, and also the statistics of the energy release rate. So here is just an example of the sort of initial random C field that we have. And I've got a mover here. Let's see if I can play using this tool. So this is what we get from the flux rope dynamo. So just a tangling and a stretching of our field. It's colour-coded, so we go from blue, which is quite weak field, to yellows and red, which is very strong field. The actual simulations that we perform, the density of flux rope tends to be a little higher than this. It just makes it very difficult for visualization. So I've sort of reduced the density of flux ropes in these simulations. I'll get off this. Let's have a look.
You open the can of worms.
Oh yeah, exactly. Aha. So we've got this idea that the dynamo is a machine, so it's converting mechanical energy into heat. And what we want to know is our flux rope dynamo a more efficient machine, taking the kinetic energy and pumping it out as heat. And so we define two energy release rates, one from the induction equation, which we call gamma I, Fred's phone's connected, and one from our flux rope model, where we consider the amount of magnetic energy that's released in reconnection events divided by the total magnetic energy. And we do something similar in the induction equation as well. So here we've got a log plot on the log scale on the y-axis. We've got our energy release rate from the induction equation and from the flux rope model. And we can see we've got about an order of magnitude difference. This line here, this white line, is just the mean. And we can also see we've got a much noisier signal from the flux rope dynamo compared to the very smooth signal from the induction equation. So the first point is this order of magnitude difference in the models. Now we're not at Rm tends to infinity in the induction equation simulation. And so without doing anything to the velocity field, the growth rate of the flux rope dynamo would be slightly higher. So to make everything fair, we scale the velocity field slightly, just with a small prefactor less than 1, just to make sure the growth rate of the two dynamo is the same, to give the induction equation a fair chance. But we get this order of magnitude difference in terms of the energy release rate from the two models. We also have a much more interesting statistical picture. So solar flares are known to follow a power law, and there's a really good review by Charbonneau, which gives values from satellites and these sorts of things, ranging between 1.5 to 2.6. So the probability of high energy reconnection events is obviously much lower than the probability of low energy reconnection events, and you get this sort of power law. And once you've got a slope of less than -3, you've got this nanoflare model which Parker proposed, where the energy released by the small flares dominates over these large events. Now there's no dynamo in the solar corona, but it's just interesting to put our new model on with some sort of perspective from the literature. And when we do the analysis of the time series, which I showed you here, we get a slope of around -3.3 from our flux rope model. Here we've got the same statistics from the induction equation, and we've got a Gaussian fit here. Well, it's -x squared, so Gaussian once you come out of log. And we also get very similar results, a slope of around -3 for the ABC flow, and a slope of around -3 for the non-linear model, which I'm going to introduce in the next couple of slides. This result seems fairly robust. So the next step, really, once we've done the kinematic runs, is to try and introduce the non-linearity into the system. And so our starting point is the Lorentz force here, which we write as J cross B. We can write it as nabla B curl B, nabla B cross B. And then we can just decompose this and make use of vector identities to get down to this guy here. We've got the tension force and the magnetic pressure, these I think have been shown. Now our magnetic field is confined to these thin flux tubes, which at each section act along a tangent, and so we can just pop this in here and we get two terms. One which is B squared times the curvature, and one which is the sort of anti-pressure term, which cancels with the parallel component of the magnetic pressure, and we assume that the perpendicular component of the magnetic pressure is going to cancel with the gas pressure. So the only term that we take from the Lorentz force is just this curvature force, which is B squared times the local curvature. We take this and we pop it into the Navier-Stokes equation, where we've assumed no viscosity. Our pressure is balanced with the perpendicular component of this magnetic pressure term. We've got the advective derivative here, and we've got this sort of forcing term, which is trying to make the flow like the Ks flow. And now we're going to consider two limits of the non-linearity. In the first limit, we're going to allow waves to propagate, so we're going to allow velocity fluctuations, and we're going to say that they're much larger than this forcing term here. So we just get down to du by dt is equal to b squared times the local curvature. And if you go through the maths, you can show this will generate alpha waves. So what we do is just see if these can be reproduced with our model. So we've got a single flux tube, which you string across a periodic box, put a small perturbation in, and let the code run. And we get this sort of thing here. So again, going wild here. So we get this nice wave solution. And we've not really done much work on this, so it's going to hit the boundaries. There'll be an interaction at the boundaries, and then the run stops. So there's obviously a lot more to do with this, but we've pursued the dynamo-related case, really, and tried to filter waves out. So that's something that we will come back to in the future. So I guess that should work. Yeah, so now that we've introduced waves, we try desperately to get rid of them, because in a full simulation, they're very difficult to resolve. And so we set du by dt here equal to 0, so not allowing fluctuations in the velocity. And we get down to this, where it's very similar to this ambipolar diffusion saturation that Candu introduced in, I think, his second lecture. So we've got u is equal to UKS plus some relaxation term here, tau, times b squared times the local curvature. And we've got a very small value for this tau, but b initial is set to be 1, and so b becomes quite large, and the dynamo saturates when this term becomes roughly comparable with UKS. And I've got a simulation here on the next slide, where we see we've got no boundary conditions. We've set up an initial tangle. Velocity field acts, and we've got this curvature force in here as well. And once the dynamo saturates, it just sits there. So it looks like there's a suppression of turbulent magnetic diffusivity. So I emphasise there's no boundary conditions in the simulation I'm going to show you. The flux tubes are free to go anywhere in free space, but they just seem to be confined to a region. And the run is over sort of 100 large unit turnover time, so it's quite a long run, and it saturates very early on here. And over this long time period, there's no dispersion of these flux tubes. So I have to jump out of Beamer, because I like to add music to at least one of my movies, and it always seems to cause problems with Beamer. So let's see if we can have a little bit of Chopin to soothe the soul. Playing Fred's album collections here. Here we go. Maybe I didn't want to do that. Something will play.
No, it's trying.
It did play. Lovely. So you see the dynamo saturates very quickly. We're already in the saturated phase here, and this will run for quite a while. And any time that the loops try and break off, this curvature force just kills them. So you see small little adventurers try to break away from the main tangle, and just very quickly.
Destroyed by tension, right? And then by convection.
Yes, so the curvature force kicks in. There's reconnections taking place all through the bundle. It's just very difficult to see just with just your eyes on these simulations. If you look at the number of reconnection events in a simulation, it's typically the order of, say, 100,000. It's a lot of reconnection events. So we go back to Beamer. So, whereabouts are we now? Not there. So what we look at now is just the scaling of the curvature in our simulations. So the first thing is we look at just how curvature itself is distributed. And Shekachika et al. Did this with the induction equation in a spectral code and showed that probability distribution of kappa, the curvature, scales like kappa to the minus 13 over 7. I think we derived this analytically and showed it in their code. We also showed that in the kinematic regime we get this let's phone again. We get this scaling. They also showed that the modulus of b times kappa to the half was roughly a constant. So kappa b squared scales a constant. And they also showed that this minus 13 over 7 scaling persisted in the nonlinear regime. We agree with this here with our results, but disagree with these two parts, which I'll show. So this is the results as obtained in the Fluxrope code. So we've got log-log scale, and we've got this nice minus 13 over 7 here. And so this appears quite robust from the analytic work that they do in the paper. But in our simulations, when you scale b and kappa, you find that it goes like b kappa to the third. And this looks really bad, this plot. First you've got these jumps because the modulus of b is always 2 to the n. But if you actually I had a little plot and actually plot a little probability density functions on each of these, and the fit is actually not as bad as it looks, I'm honest. It's actually not too bad, so what, 10%, something like that. So, and this scaling of b kappa to the third was also showed analytically and numerically by Leonard with the ABC flow, and he just considered the passive lines, but stretching in a very similar manner to what we get. Now, why this is important is because of the way that the magnetic tension force scales. So, just on simple dimensional arguments, you've got that the tension force goes like b squared over L, which is like b squared kappa. And so, in the simulations of Shekachika, when they got mod b kappa to the half, roughly a constant, their tension force, you could say, is not sensitive to the curvature. And maybe that's an explanation for why their folder structures remain persistent in the saturated dynamo. With our b kappa to the half being roughly constant, you can run it through and you find that the tension force is sensitive to the curvature. So higher curvature is subject to the strongest tension forces. And when you look at the spectrum of curvature as the dynamo saturates, you find you get something like this. So this is roughly minus 13 over 7, but with saturated VRMS plotted here. And you can see that just as the dynamo saturates, there's quite a steep drop in the slope of the curvature. So you've got less and less areas of high curvature, and then this appears to roughly saturate. These exponents were fitted just with a simple MATLAB code, which maybe explains why it's quite noisy. Going in and fitting these lines of best fit, sometimes it needs a human eye to pick where to put them. But it appears to roughly saturate. And so we have this drop in the exponent. And so, like I say, there's less and less areas of high curvature in our simulations.
Sorry, can you illustrate just the sketch on the blackboard, what you mean? What happens?
Yes, yeah. So, if we have something that's very folded like this, where there's regions of high curvature, we've got the magnetic tension force, or the curvature force as it is in our simulations, acting to remove these folds, and so creating a smoother structure. So
the folded structure is
appears to be destroyed in the nonlinear regime, which is something that Shekachika et al. Didn't seem to find in their simulations. But I don't know, I think in higher resolution simulations now, they see less of these folded structures anyway.
Even they?
Pardon?
Even they?
Yes, yes. Where I'll finish is just going back to why we didn't consider the mean field dynamo or large-scale dynamo, is because magnetic helicity is currently a bit of a problem, because we're modelling these flux tubes as discrete lines, and so they can't have any form of twist. And if you look at the papers of Moffat and Rika, you see that twist can have, the magnetic helicity can come in different forms, and one of the key forms, I guess as Kanu's explained as well, is the twist of the flux tubes. And although we have a tangent vector to our discrete lines, we don't have a normal vector. And so a normal vector that rotates with the flow. And so we can't define twist properly. So something that we're currently working on at present is to try and either use a model of ribbons to try and look at what happens to twist, or just to look at the effect of the flow on the flux tube. And so something I'll finish with here is just when we consider a flux tube as a ribbon where we've got the top and bottom as red and blue. We've got here, just before a reconnection, all that's active, we've just got the magnetic tension force that just drives these two loops together and causes a reconnection. And if you look very closely, it's probably quite hard to see, but after the reconnection, there's an overlap, so you've got red over blue and then blue over red, and similar here. And if here you had a linking number of 1, say, between the ribbons, afterwards you could go in and you could work out both the ride and the twist using the Caligrano theorem, which I popped on here. And you can show that helicity would be conserved. So we'd have a linking number of 1 here, and so a helicity of 2 times the flux of the tube squared. And here, I think when you go in and do it, you get roughly a ride of order unity and a twist of unity. And so the helicity is also 2 times the flux squared. So future work with the model. So there's more to do with the saturation mechanism. Magnetic helicity is something that we need to look at, and that's something that I've been working on with Kandu while I've been here. There's a possibility of trying to include magnetic buoyancy, so we can actually use this as a model for the solar corona. So it would just be driven by random foot point motions. We'd have the same sort of reconnection algorithm. We've got alpha waves that we've hardly touched on. We just sort of showed that the model could produce these alpha waves, but have not considered the wave cascade. And finally, obviously, a very long-term thing. I just put it here because Carlo loves this, because he's sort of interested in these quantized vortices. That in neutron stars, there's a superfluid core. The neutron stars rotating, so you get a lattice of quantized vortices, which can become turbulent. And these vortices also entrain protons, and I think protons entrain, if someone knows correctly. And so you get a magnetic field aligned with these quantized vortices as well. So you'd have the possibility of alpha waves and Kelvin waves propagating along them. So it's sort of like I've merged my 2 supervisors, so taken sort of what they're both very interested in into this one model, but that's something that I will not be looking at for a long time. And I'll just pop a few references up. If anyone's interested in anything that I've talked about, come and find me. And that's everything. Thank you very much for listening.
The question was about the initial conditions.
With all the simulations, I mean, one thing I actually didn't mention, which I should have done, is that all the loops that we consider are just closed loops, just to conserve the divergence-free magnetic field. But in all simulations, it was something roughly similar to this. So just a random weak C field in all simulations.
Is the power spectrum k to the 4th?
Well, yeah, something like spectrums is never something that we've looked at with us.
Next question?
So, in the simulation, the flux, the magnetic field is attached to the KS particles.
Exactly.
To the field. So the curvature you were talking about is the curvature of the motion of those particles.
Yes.
So it turns out to be minus
13/7.
Okay, 2 and as compared to what you just evolve a simple KS, I should know. Like that. Without magnetic.
Well, the magnetic, this is it's in the kinematic. This minus 13/7 here is where. Oops, I've gone way past it. This is in the kinematic regime, so the magnetic field has no effect on the flow.
Oh, it's just the way the flow was constructed.
But I think this minus 13/7, when it's derived in the paper by Shekachikin, I think they use a Kazantsev type model, and they also get the same sort of scaling.
So that's my question. What has it to do with the Kazantsev thing? Is the magnetic field not involved? Is it involved? Yes or no?
In this minus 13/7 scaling, no, there's no.
Is this the curvature of magnetic lines?
Yes. Yeah.
So
All the
is involved.
Or the curvature, but it can also be the curvature of just passive lines as well.
Any line affected with the fluid.
Yes.
Yeah.
Right. So it's not a property of it's a property of the KS coefficients you've chosen in the beginning, right?
No, it's the dynamo creates magnetic field, which has this distribution of curvature.
Are you saying the same thing?
I think we do.
I think so. Yeah. It could be a magnetic field line. It could be a passive line, which is the same thing.
So can you say passive and dynamo in the same sentence? Or?
No. And the thing which you're doing differently is that whenever you stretch something, you double something, right?
Yeah.
So that is also important in the magnetic
Yeah.
field of the curve.
When you come to this bit here, when you're looking at the scaling of B with the curvature.
Oh, all right. So there is a magnetic field that is not just any point in the KS. It's
Here.
It's something that obeys that addition rule that you have for connecting and reconnection.
Yeah, but in this part here, this is just purely the distribution of curvature of the lines. So it could be just a passive line.
Streamlines don't reconnect, right? Unlike magnetic lines, streamlines would not reconnect. And streamlines won't have doubled strength of the field. So it is important that these are magnetic lines.
The only reason why I'm asking is something I know about is if you have particles that move in a turbulent flow, the curvature has to go like -5. Okay, that's
Minus 5
no -5 half.
5
Yes, that's the statistics of curvature of Lagrangian particle path in a turbulent fluid. All right, so it appears to have changed from -5 half to -13.7, and that's the result of reconnecting. Is that I was asking? Is that what you're saying? Okay.
Do you think this is universal? It's supposed to be independent of the velocity field that you produce.
I mean, like I said,
it's specific with the velocity field you've chosen.
It's not specific to the KS velocity field because for the derivation in the 2004 paper, it was of Shekachikin. It's certainly not KS. I think it was Kazantsev.
Kolmogorov flow, red and
Yes.
white.
No, it was single scale flow. Kazantsev model is a single scale flow. It's 237. It's controlled by the dynamo. But not by the velocity.
Bon.
I never looked at it in the ABC flow. I never looked at that.
It would be easy to do though,
It
right?
would be easy to do. Yeah.
Yeah, it would be interesting.
But the energy release rate, statistical energy release, seems to be universal. It's the same in the KS flow or ABC flow. Very different flows, still the same statistics of the energy release rates.
I mean, the energy release rate in the ABC flow is much lower just because the growth rate is much lower than I don't know what the growth rate is for the KS flow, but it's higher. But it's a similar sort of order of magnitude or just under an order of magnitude higher than the ABC flow. Paul?
Okay, if there's no further question, thank Andrew again. The opportunity to go now up to the observatory, 1 meter telescope. Please follow our journey way.
Don't think I'll be with me.
Vai haluatko olla toisessa ryhmässä ja niin, että päivä on
Well, we did it. Our project was completely completed. It was, yeah, it was nice. Well,
Very interesting.